Kyle, an 85-kilogram football player, leaps straight up into the air with no horizontal velocity to catch a pass. He catches the .430 kilogram ball precisely at the peak of his jump when he is .386 meters off the ground. He hits the ground 0.037 meters away from where he slept. If the ball was moving horizontally when it was caught, how fast was the ball traveling? And as is usually the case here, we'll start off by drawing some pictures. So we have, obviously, the ground. And Kyle has leapt up in the air, but he has no horizontal velocity because they tell us that. And he has no vertical velocity because he's at the peak of his jump. So he's basically at rest. Meanwhile, there's a football coming in. Oops. I'm going to call the velocity of the football v1. And then Kyle catches the football, essentially having not moved at all during the collision time. So he's holding on to the football. And now it starts moving, or it starts moving with the speed I'm going to call v2. Actually, I'm going to draw that a slightly different place. Let's put the football back. And I'm going to say that together they're moving with speed v2. But they tell us that Kyle is a height h off the ground, and that he then travels and lands. We know he travels parabolically, and he lands a distance r away. And for completeness, let's also put in the mass of the football is m1, and the mass of Kyle is m2. So, while he's catching the football, during that collision, there's essentially conserved, there's conserved momentum. And so we can say that his initial momentum equals his final momentum, or the system's initial momentum is the final momentum. So, there we go. So that P initial equals P final, or M1 V1 equals M1 plus M2 V2. Unfortunately, we don't have V2, so we're going to have to go and find V2. We're going to do this kinematically. We're going to say after the collision, Kyle and the football travel as a projectile. And so we know that there is, that we have horizontal positions that look like this. That x is x0 plus v0 xt plus 1/2 a xt square. But he ends at a position r. We're going to take our origin as being right here. So he ends at a position r. He starts at a position 0. He has v2 as his speed times t. Let's say t final. And then he has no horizontal acceleration. So, as has happened many, many times before, this simplifies to saying the range is v2 times his time of flight. How long is he in the air? Which means that we could get that v2 is the distance he travels over the time he falls for. Unfortunately, while we have this, we don't have this. So we have to go a little further and say, well, how do I get that? Well, if we look at the vertical motions, then we have that y is y0 plus v0 yt plus 1/2 a yt square. And we know that he ends on the ground, but he starts at height h. They tell us he has no vertical velocity at this point. Well, I guess we should say here, he has no vertical velocity because the vertical momentum of the system before was 0. Nothing was moving up or down. So the vertical momentum after, right now, is 0. Then the Earth acts on him and it gets a little crazy. But during the collision, he has no vertical velocity. But he does have an acceleration downward at g, and therefore it obeys this equation, which tells that 0 is h minus 1/2 gt final squared, or t final is 2h over g square rooted. So I can go back to my original problem way back when and say that stuff I know, m1 v1 is m1 plus m2 times v2, but v2, remember, was r over tf, and tf is this thing, 2hg over g square rooted. So when all is said and done and we do our solution, we end up with that v1 is m1 plus m2 over m1 times r times square root of g over 2h, which is a bit of a mess, but we can just plug in numbers, so we'll do that. So v1 is, let's get our numbers right, 0.430 kilograms plus 85 kilograms over 0.430 kilograms times the range, which, let's see, that is 0.0371 meters times this fraction, square root of g, 9.8 meters squared, times 2 times the height at which he jumped, which was 0.386. And this comes out to be 26.2615. It looks like we've got 3 sig figs everywhere, so 26.3 meters per second. And that is our answer.